Hello, everyone. Thank you so much for welcome to our talk, and thank you so much for staying for the closing notes. My name is Cfir Cohen. I'm a tech lead on Google Cloud, and co-presenting with me is Josh.
Yeah, hi. I'm a tech lead on a team called Virtualization Security and Cloud.
And we also have in the audience James Forshaw from Project Zero, who has been involved in both security reviews that we'll be presenting today. So we know we stand between you and the end of conference plan, so we try to make it interesting. And by the end of this talk, you'll have better understanding of confidential computing, what it does, what it cannot do. You'll have a better understanding how it is implemented by two leading CPU vendors, Intel and AMD. We'll share some of our experience doing security audit and security review on both the AMD SNP implementation and the Intel TDX implementation. We'll share our methods, tools, and also a few very cool findings. So for background, we had this actually privileged access to both, as Google as a cloud provider company, we had privileged access to both CPU vendors, and when they introduced a new technology, trusted, called confidential computing, and we'll define confidential computing in a minute, we had an opportunity to sort of help the vendors build trust in this technology, right? Because when you talk about secure processing and confidential processing, it's all about trust. How do we build trust? How do users build trust in a technology that is developed by company A and deployed by company B? So trust is key here. And there's a very nice paper, academic paper, linked here in the slides, that talks about the role of a third-party security audit and how it has to be public, how it has to be transparent and shared with the audience, with the public, so they can independently verify the implementation is correct and secure, and therefore build and establish trust in those systems. The how is we engaged with the platform security teams and the security architects on both vendors. This was a white box security audit where we had access to documentation, source code, and most importantly, access to humans and engineers. So we got to engage and ask them questions about how the system works. Have you tested this edge case and so on? It was impactful. In total, we reported dozens of vulnerabilities. Some got CVs, some were actually fixed before the technology was published and deployed in production. So this is the best case scenario, right? You find a bug and you fix it before it hits production. And the two audits and the two reports were published, one last year and one just recently, two months ago, one on the AMD SNP and one on the Intel TDX. I really want to take a minute and acknowledge the great effort and work from my colleagues. We have folks from Project Zero. We have James, Jan, Mark, Felix, and Erdem from Cloud Security. And I also want to acknowledge the awesome firmware and CPU designers. I know this is in somewhat contrast to the keynotes, right? In the keynotes, Rodrigo talked about how we found bugs, and we're sort of chasing PCERT, and we're trying to get the vendors to fix issues. Here we had a really close collaboration with the vendors, and we really had a chance to see how system architects think and really appreciate the challenges that they're facing. Because at the end of the day, we need to make this work under a tight cost structure, right? It needs to be manageable at scale. So I just wanted to pause and acknowledge that too. All right, so what is confidential computing? In essence, this is a hardware-based, so this is a hardware security conference. Confidential computing is a great fit. It is a hardware-based trusted execution environment. So folks who have background in trusted computing, like secure boot and measure boot, this is a natural extension to trusted computing. Folks who work on sandboxing, a confidential computing environment is a reverse sandbox. And for folks who work on virtualization and cloud technologies, confidential computing can be viewed as a bare metal solution, right, where customers get a slice of hardware and they can run their workload in an isolated environment. We have two main features from confidential computing. One of them is remote attestation, and this is where you get your initial security guarantees, right? You have an attestation, which is a signed report, signed by a key held by the hardware, that measures all the code and data pages loaded into the enclave, into this isolated environment. And secondly, you have this strong isolation property where the enclave is protected from its hosting environment. So you have protection from the hypervisor and the virtualization stack. You have protection from peripheral devices and also co-located tenants. In many ways, and this is why I'm very excited about confidential computing, this represents sort of a paradigm shift because you know the meme that cloud is someone else's computer? With confidential computing, that's no longer the case, right? We're giving control back to customers. They have a minimal and well-defined TCB they can reason about, they can verify, they can audit, and therefore they can trust. And it also enables new use cases. First, it enables protection of data in use. So you're probably familiar with protection of data in transit and at rest. With confidential computing, you have protection of data in use. So you can build policies that are centered around code identities, and not just human identities or other kind of more ephemeral certificates and identification methods. It has all the hallmarks of an innovation trigger, right? Today we see a compute model that supports VMs. So we have confidential VMs, which really simplifies adoption, and it also supports lift and shift. It supports lift and shift. Furthermore, it is available across multiple vendors, like CPU vendors, and across multiple cloud providers. So this is not a niche technology anymore. It is young, but it is becoming mainstream. This is I think why I'm so excited about working on confidential computing, and why we're also inviting you to participate. And finally, this is also an enabler. Confidential computing enables new kinds of use cases, and the biggest example is data clean rooms and multi-party compute, where you can have computations that sort of can handle data from multiple parties and only return the aggregated result, right? Knowing it's fully protected from tampering and compromise. All right, the threat model is super interesting here. So in many ways, we're trying to deprivilege the host operating system. Up until now, OS is trusted to not only manage resources, but also have access to those resources, right? Scheduling, memory management, emulated devices come to mind. But with confidential computing, the operating system is only trusted for resource management and not for any kind of access. And the adversarial model here is the host operating system is a very powerful adversary, because when you think about it, there are many components on the host that could be tampered and controlled by an untrusted adversary. That includes the host firmware, which is by definition not trusted in confidential computing. And in practical terms, it means that the confidential computing environment needs to defend itself against all kinds of bad system configurations. There's also a large API attack surface, and almost by definition, there are two kinds of attacks that a deprivileged resource manager can still mount, and that's control over scheduling and all kinds of memory access oracles. Because when you manage those resources, say you manage a memory page, the host can at will unassign that page from a confidential computing environment and sort of get exceptions when the guest tries to access that page. So you have these built-in access oracles, which are almost by design. I'd like to point out that physical access attacks are not in scope for confidential computing. So no DRAM interposers, no voltage glitches, but malicious DMA and malicious peripherals are in scope. So we'll see some security controls that defend against that. All right. So quick background. So we'll cover the AMD-SNP review. AMD-SNP is anchored in the PSP or the ASP, the AMD Secure Processor. The ASP is an isolated execution environment that hosts security-critical workloads. It is embedded on the SOC, and it hosts the SEV firmware. The SEV, the Secure Encrypted Virtualization firmware, this is the brains behind SNP, right? It does all the guest management logic. It does the nested page table management. It manages the page ownership table. And it also programs the inline memory encryption keys, and it signs attestation. The hardware components, other hardware components that are sort of interacting here, part of the solution, is CPU microcode. The CPU microcode on every store, this consults the page ownership data structure and validates ownership before it accesses DRAM. We have the IOMU. IOMU normally translates IOVAs to host physical addresses. The IOMU also verifies page ownership before any DMA write hits DRAM. And we have the memory controller that performs the inline AES encryption. The pages, the definition of which page is private or public is done by the client, by the guest environment, right? So the best way to think about it is that there's full control in the client. It fully controls what kind of data it wants to share with the external environment. So with these two properties, with the ownership check and with the memory encryption, we have integrity guarantees and we have confidentiality guarantees. These together form the confidential computing environment. We've had a chance to audit the system for a few months, and I think that the biggest message that we would like to share is that there is a systemic way to find high-quality bugs. The things that worked well for us during the research are the following. The first is invariant analysis, right? When you deal with complex systems, it's really important to understand the threat model. Yeah. Thanks. Invariant analysis. So things that work well for us is to define the threat model, define the kinds of security environments the system tries to maintain, and then to audit the system holistically, right? So not component by component, but holistically, and verify and check how the system maintains those security invariants. So for example, when you assign a page to a new owner, to a new guest environment, you want to make sure that all the cache lines have been flushed from the CPU. This is an invariant you want to maintain. Another thing that worked well for us is crypto-related security reviews. So the SNP is the SEV firmware is a crypto-heavy application. And I personally think that doing crypto-related analysis is a superpower, right? Once you know it, you find it everywhere. And there's a good methodology behind it. So when we audit crypto-heavy applications, we're thinking in terms of layers, right? From the core primitives, the base implementation, then the algorithms and encryption schemes or signing schemes and so on, and then the high-level protocols. Another thing that worked really well for us is to really focus on places where the designers traded security for performance, right? This is actually common in compute environments where there's a lot of emphasis on performance. So anytime you see a performance security trade-off, you know you're going to find security issues, right? So this has really guided our analysis. I want to call out two tools that really aided our analysis. One of them is the WitcherProof, which is a database of test vectors for cryptographic libraries. And another one is a PCIe screamer, which is used to send arbitrary packets on the PCIe traffic. I'll show a screenshot in a minute. All right, just quickly, our approach to doing cryptography-related reviews is to think in terms of layers. When we audit the implementation, we look for things like correctness. Does it handle all the edge cases for a primitive correctly? We're looking at the source of randomness, and we want to make sure that there's no bias in any random selection. We want to make sure that the implementation doesn't handle sensitive data in non-constant time, right? And I really want to call out that when attackers target crypto implementations, they target implementation, right? Not the map. The second layer is the algorithms, how those building blocks are sort of assembled together to form, say, an encryption scheme or a signing scheme. And this is where you look for weak signatures and weak modes of encryption. And finally, the protocol is how you assemble those algorithms, those basic block algorithms, together to form a secure channel. And the security properties that you're looking for when you audit cryptographic protocols is, of course, secrecy and confidentiality, but also authenticity, freshness, and strong identity binding. And I think we saw some example from previous talks that showed how the Fitbit didn't have those strong identity binding in the protocol. All right, so now a couple of findings from the S&P report, and you're welcome to look at the public report and find all the details. I think this is my favorite bug in the S&P audit, my favorite crypto bug. So when you think about it, the enclave doesn't trust external storage. So when the SEV firmware doesn't trust external storage. So when it needs to maintain state across shutdowns, it needs to securely serialize its state and protect it when it's being written to external storage. The persistent storage encryption key was authenticated, so that's good. It used AES and EdgeMac for integrity validation. But when you look at the details, and details matter, when you look at cryptographic implementations, details matter. We noticed that the SEV firmware used a fixed IV. And a fixed IV in the AES counter mode means that you always get the same kind of key string. We can sort of see it visually here when we dumped two persistent storage blobs. And you can see that when their data didn't change, the ciphertext didn't change. Right? So this is a big no-no in cryptography. So what can you do with this? The first idea is to find ways for the firmware to write known code, like known plaintext, and store that in persistent storage. Imagine the firmware starts up with an all zeros state, and it writes to external storage. Luckily, the SEV firmware didn't do that. But then we realized that if you somehow compromised a private key, which is also stored encrypted here in external storage, and we did find an invalid curve point attack back in 2019, which was fixed, you could actually recover the key stream and then use the recovered key stream to also compromise private keys generated by fixed firmware. Right? So this is a bypass to another cryptographic-related vulnerability. And this is very common when you audit cryptographic applications. One bug would sort of magnify the impact of other bugs. And the reason I enjoy doing this cryptographic-related audits is because when you find a vulnerability, those are the stealthiest kind of vulnerabilities, right? No one can detect a compromised signing key. Unlike, say, looking for heap shaping attacks or crashes or whatnot. All right, the second finding involves a hardware component. So to recap, there's this highly privileged data structure called the RMP, which maintains page ownership for all physical pages. And when you sort of think about all the components that target or sort of read from the RMP or write to the RMP, you realize that there are three main components. There's the SEV firmware running on the ASP. There's the x86 microcode that does the page ownership check on every store. And there's the IMMU that also does the page ownership check on every DMA writing. Right? We also realize that this is an example of invariant analysis and an example of a performance security trade-off. We also identified that these RMP entries are cached by the x86 core in the TLB entries, and they're also cached by the IMMU in the IO-TLB entries, which means that now we have a new invariant. We need to make sure that all these caches are coherent across all the components. So when the RMP changes, you want to make sure that that change is reflected in all the caches. Or in other words, you want to make sure that the cache is invalidated on every update. So when we looked at all the update flows, we found that, yeah, x86, whenever it updates the RMP, it invalidates the IO-NMU TLB, the IO TLB, so this is correct and safe. But then we also found that there's a path in the SNP init API where the SEV firmware updates the RMP but doesn't invalidate the IO TLB, which means that you could sort of spoof the, you could poison the IOTLB before calling the SNP init function and get those components to be out of sync. Get the IOMMU to think that page X is owned by the hypervisor, but then the RMP actually converts that page to be owned by the firmware, and by having those stale IOTLB entries means that you could overwrite it, DMA over private pages. So this was another high-impact vulnerability. And here we used the PCI Screamer, which is a PCI device that can be used, which can be controlled over USB and can be used to both monitor the PCI traffic and send arbitrary bytes over it.
Cool, thanks. So that were some of the highlights from the S&P review that we did. Starting kind of late 2021, we did a separate review with Intel on their solution called Intel TDX. Specifically, this is kind of their initial launch of TDX, so it's TDX 1.0. There are kind of already 2 follow-up specs that they have. To give you kind of an overview of what TDX is, it's, a lot of the things are pretty similar to what we were just hearing about for AMD S&P, but there are some differences. So if you think about what kind of virtualization looks like in a nutshell today, you have a VMM. This is kind of a minimal version, right? But you have like some hypervisor below all this, and you have your regular VMs, and there's some kind of isolation between them. So TDX, and this is a diagram taken from the TDX spec. So TDX adds a few extra pieces here. So now we have the VMM, it has some like TDX awareness to it, but the big changes are we have this TDX module, and this is code that Intel writes and signs, and it gets loaded, and it's kind of like an interposer between your VMM and these trust domains, which are the kind of confidential VMs that Intel has created. So the trust domains are regular VMs, but they have some enlightened drivers that know how to talk to TDX module. The other critical piece here is that the TDX module is running in SEAM mode, which is a new execution mode. It's very similar to just regular x86 mode, but it has a couple extra privileges. I guess think of it kind of like SMN, right? It's just another mode that has additional privileges. But it turns out this is kind of just one piece. There's a bunch of supporting cast members here. Some of these are legacy technologies, and some of them are new. So at the bottom, kind of we have the platform level things, so right, microcode, MSRs, Uncore, all these different things help support TDX. MKTME is the multi-keyed total memory encryption, I believe, and that handles the kind of memory encryption for these trust domains. And then on the right side is kind of the boot flow and kind of initialization flow. These are all the different pieces that get you up and running and get TDX into memory. So all these are important to kind of think about when you're going and trying to review TDX. We'll talk about a lot of these in more detail in a second. So kind of a rough trust boundary here, right, is if you're running TDX, you need to kind of trust all these Intel-provided modules. And I should also say that most of these are open source, or at least the source has been published, so we'll talk about that at the end. So, you guys can go verify yourself. We went and verified ourselves. But that's the trust boundary, kind of. And then if you look at, what are the different attack vectors, some of them are here, right? So like Cfir said earlier, the BIOS is untrusted, OS is untrusted, SMM is untrusted. So all these different places are viable attack vectors into all these trusted areas. This should also show it doesn't have, but the TDs aren't trusted, right? Like the VM, you could have a malicious TD on here, you could have a malicious VM, and there's different attack vectors there. And so yeah, same as the S&P review, if you want to see all the details, please go see the paper. We'll talk about 3 of the kind of most interesting bugs today, but there's also other bugs found in some of the other modules. Yeah, so the strategy here, like I kind of mentioned, we had a couple different things that we focused on beyond kind of the S&P or kind of learning from the S&P review. A lot of this was, in Intel's solution, they don't really have anything kind of exactly the same as the PSP, so they have a lot of legacy technology and this TDX module. And so a lot of our focus was like, what has changed between legacy and TDX, and let's go focus on that. The other thing that changed was there's a lot of legacy technology that was designed for an old threat model, right, where maybe the BIOS is trusted and SMM is trusted, but now they're using those same technologies and applying them to this new threat model, so we need to make sure that they still hold up. And then, the actual work, we applied, a variety of techniques. We had manual code review. In this case, we didn't actually have hardware implementation. This is pre-hardware release, so we had kind of a simulation environment that we used that Intel provided. And then we used some of the same kind of strategies that we learned from S&P that Cfir mentioned as well. And there's a link here if you're interested in the full report. So to start with, just to give you some more context of kind of how TDX gets initialized, it's similar to Intel or to the AMD model, where there's silicon-fused public keys that verifies MCheck and ACTM. These are kind of just initialization and validation modules from Intel. The bottom here is kind of a rough flow of kind of how the trust, this trusted boot sequence happens. But basically the BIOS kind of loads up this MCheck and ACTM modules. Those verify that the BIOS has at least configured the system somewhat securely. Unfortunately, these two modules are not open source, and they were kind of outside the scope of what we reviewed. But they, we talked to Intel, we got a pretty good feeling. They check a lot of things that we thought they should check to kind of make sure that you're in a secure system. And we'll talk more about that later. And basically you have this, secure boot chain like you're used to. Going NPC Motor, PC Motor, TDX module, which eventually loads your trusted domain. And also, just something of note, there is this whole attestation part of TDX, but this was outside the scope of our review. So that's done by XGX. We didn't really look into it. I would recommend other people, you should go look into it. So going back to this, the first bug we'll talk about is an NPC Motor. If you remember from this, it's like kind of the first module loaded from the OS, and so OS or the VMM is able to attack this. Yeah, that's what I just said. So the NPC loader is this non-persistent seam loader. It's basically, and if you remember, seam is this new execution mode, so this is kind of the first stage that just bootstraps the next stage and eventually bootstraps TDX, which loads in seam. It's bundled as a thing called an authenticated code module. I was not really familiar with these before, but this is a legacy technology from Intel where they can sign binary blobs and you load them at boot time. So I think things like BIOS Guard, SNED, there's a few of these ACMs that are laying around from Intel TXT, not TDX, but TXT. And they kind of leverage that technology again. So now there's another ACM called NPC Loader. One thing of note here is that all ACMs run with the same privileges. So NPC Loader, it has extra privileges because it runs as an ACM. We'll talk about some of those. But also any of these old legacy ACMs kind of have the same privileges. So finding a bug in these old legacy ACMs that are loadable on a TDX machine may also let you compromise TDX. And so yeah, it lets you, when you're running an ACM, you have some extra privileges to these registers that are used to do attestation. And also setting up these memory ranges that are basically protected ranges that keep you from writing to the TDX module. And yeah, so because of this, breaking NPC Loader breaks the rest of TDX. But if you start looking at it, it's really a very small attack surface. There's almost no user input. So at first we thought this was probably not a very interesting module. So yeah, we started looking to see what kind of attack vectors there are. The way the ACMs work is there's this instruction called GitSEC, and there's a couple like sub-ops for it, and one of them is this enter ACCS. And that transitions you from your host OS execution environment into the ACM. This instruction, this technology is old. It was designed to be used from a BIOS, was my understanding, and that's running in 32-bit mode at this point when you would call these. But the same technology is used here, but now we're in a 64-bit OS. So there's extra entrance and exit paths. There are kind of new entrance and exit paths that have been added to the NPC Loader to help you transition between 64 and 32. So this will become interesting in a bit. The other aspect here is that it runs in a constrained environment, which definitely helps some of these security, like helps beef up the security of an ACM. So some things that it does that make security a little bit, like it make it harder for you to attack an ACM, is that SMT isn't disabled. So like hyperthreading is disabled. It runs entirely from the L2 cache, and so you can't have like another core trying to poke the memory where ACM's running. It's all in cache. And also critically, interrupts and exceptions are disabled, right? So you don't have to worry about when you're running the ACM what happens if an interrupt comes in. Does it handle it safely? Because that's kind of complicated to do. They're just disabled the whole time. So all this sounded good, and then we started asking questions to Intel about like how exactly are you disabling interrupts and exceptions, and we dug into how that's done. So this is a sample. This code is all published on Intel's website. This is the assembly for the entry to the ACM. There's a lot here. I've commented out, I've removed some things to make it fit on here. But essentially what happens is on entry, it sets up the IDT. I think it saves off your old IDT. And then basically the way that you can disable interrupts on x86 is by nullifying the IDT. The IDT is the interrupt descriptor table, which is basically like a vector of function pointers to, get this interrupt, call this function. So that's what they're doing. They just disable interrupts at the beginning. You pass in a few arguments to the ACM through different registers. So like they save off with like original GDTR. They save off some other fields. Then the kind of cloud in the middle is just, the actual logic for NPC Motor. And then on the exit path, they basically re-enable interrupts, restore your GDT, restore kind of some other CPU state, and then this GitSEC exit AC does the actual final transition back out. So basically the entire program has no interrupts enabled, except for this little tiny bit at the very end. So we started looking at that because it's like, it doesn't really look like much there. We started looking at each instruction to see if there's anything that could actually trigger an interrupt, or in this case an exception. And the LGDT, the attacker, which in this case would be the OS or the VMM, does pass in this value. And it turns out if you look at the Intel manual, if you pass in a non-canonical address to LGDT, it does trigger a GP fault. So this is like the actual vulnerability of where we started looking and digging into kind of what you can do with this, right? So basically a user can come in and they can build up a fake IDT. This is kind of the sequence of events that you might want to do to exploit this, right? So you'd have some kind of fake interrupt descriptor table, and maybe, we'll talk about the scratch space in a second, but you need to put it somewhere, right? And then the idea is you hit this LGDT, it triggers an exception, which does a lookup in this fake IDT handler. It looks up the GP fault handler and then calls some x86 code. So you have this kind of like double jump that you're going through. So that's the idea of how to exploit this. So I guess the one thing that I didn't have here is that the way this works is there's a trick to this is when you're running an ACM mode, I mentioned that this is all entirely in L2 cache, so the attacker doesn't have any memory access to it. So getting this, and also the whole module is signed by Intel. There's like an RSA signature that covers the whole thing. So it turns out that there is a scratch space that we found in the module that's used for like RSA intermediate computations, but it turns out they don't use the whole space. And so we were able to load our fake IDT into that and then have the ACM be loaded. The signature validates, and it still triggers on the exit path. So this is a screenshot. Like I said, we didn't have real hardware, so this is the best we had. This is Simix, which is an Intel simulation tool. And there's a lot here, but basically we redirected the IDT to like I think an infinite loop that was already in ACM just to kind of confirm. And then you can print out at the bottom left, and you can see like, hey, we're still in ACM mode, which is this super privileged mode. And then if you go back to the boot flow, we've compromised NPC Motor at this point, which essentially lets you compromise the rest of the boot chain. So that was NPC Motor. There's another bug in the report if you want to see that. The TDX module is the next thing I'll talk about. This is kind of the big chunk of code that runs and manages your trust domains. So there's a lot of code in the TDX module. This is all written in C, and it's responsible for TD management. So bringing up these trusted VMs, taking them down, adding memory to them, managing out of station. There's a lot of different things that they handle, or that it handles. And there's two kind of API interfaces. There's one that's directly accessible to the guests, and there's a new instruction you can use called TD call. And there's, I think around 9, it looks like. And then on the host side, there's another instruction called seam call, and that's where the VMM can call into TDX. So we spent a good chunk of our time reviewing this code, and it turns out it's actually pretty good code, I think. We found a few issues, but overall it was pretty solid. We used a mixture of manual code review. I think Cfir mentioned before we used Weichproof to do some crypto validation. We used Wegley for variant analysis, and Promisee to do some limited static analysis as well. There's 4 bugs that we found, and I'm not going to talk about them today because there's just not enough time, but if you look up the report, you'll find them. So a couple other areas that were interesting and kind of new to the TDX threat model were looking at these like platform level hardware interfaces that the attacker has, right? So MSRs and the Uncore on Intel are basically all the configuration and stuff in the SoC outside of x86, right? There's a bunch of like the memory controller, MKTME, these are all what Intel calls Uncore. And then MSRs we're all familiar with, are just configuration registers from the x86 side. So we looked at a couple different attack vectors here. So just some overview of MSRs, right? These are writable from a malicious host, so SMM, a malicious host, which could be like OS or VMM, also SMM, and also BIOS. And depending on which of those you're running in, you have a different set of MSRs available to you. And all of those are in the threat model for TDX, right? So we looked at all those, and if you start looking at MSRs, right, there's like hundreds, if not thousands, of these control registers. How do you go about like figuring out which ones are interesting? We had a couple different strategies for doing this. One of them was we realized that there are different scopes for these MSRs. So some of them change things just on your thread, like on your hyperthread. And this diagram here kind of tries to show these different types. So like the number 1 is like here you have a thread, you change an MSR, it doesn't affect any other thread, doesn't affect any other core, it's just affecting your thread. There's also per core, which affects both threads on a core, and then there's per platform, which affects every single core. This was interesting because the second two, per core and per platform, you can change an MSR, and the TDX module has no way to intercept that or to filter it or anything like that. So the idea here is, if you're running and you hit like code in the TDX module or in a TD, all of a sudden you can start changing the system configuration out from under it. And we realize that this is kind of like a privileged inversion compared to a normal VMM, where the VMM or the hypervisor can intercept these MSR writes, filter them. I think we saw previously on the PS5 talk, they were doing MSR filtering there. So in this case, we have an alternative where the TDX module just can't do that. So we focused on these kind of 2 different types of MSRs. Actually, so I don't have anything here. We didn't find anything that was actually vulnerable, but we did kind of find different classes of MSRs within that we talk about in the paper. One of them is there's the way that in-memory encryption is done is there's physical addresses that are written with the memory key, or the key slot is in kind of the physical address, and so there's some MSRs that take physical addresses that we started looking at as well. So outside of the MSRs, the Uncore handles all the other kind of activity outside of the x86 core. MKTME does the encryption and protects the memory contents. So this is kind of legacy technology again, MKTME. But the way it works, they've taken the legacy and they've added some extra features, right? So in addition to encryption now, which is done in AES, there's the normal 128-bit blocks. There's also an integrity bit, right, to validate that someone didn't change the memory out from under you. Even if you can modify it and change the ciphertext to decrypt into something wrong, we also want to just protect it from ever being used. And that's the integrity protection bit. So there's 2 different ways to do this on TDX, and it's kind of dependent on what hardware you have. So it depends on which type of DDR5 memory you put in your system, basically, is which one of these are going to be used. So there's the cryptographic integrity, which was kind of the original design for the integrity. And this uses a 28-bit HMAC that's inline kind of in the DRAM, right? So basically the way this works is in the cache, the contents are in plain text, but when they get written out to memory, it puts the memory controller calculates an HMAC and puts that in line next to the data stored encrypted. Separately, we also have this thing called logical integrity, and that's due to kind of size limitations to this metadata space on DDR5, and in that case you end up getting a 1-bit indicator that just says this is private memory or shared memory. And the way TDX works is, the confidential VMs, most of their memory is private memory. The only memory that's shared is really like for devices, device I/O, and talking like some bounce buffers to talk to the hypervisor. So you definitely don't want private memory to be tampered with. And if someone were able to break the integrity check, that's what would happen. So we started asking about, this all sounds all right, but how would you actually go about flipping these bits? They're in metadata. You can't directly access these bits from the CPU. But things like Rowhammer let you start flipping physical bits, right? Even ones that you don't have access to architecturally. And so if you're going about doing Rowhammer and thinking about what you might do here, we have a diagram at the bottom right with these two different styles. We have the crypto integrity and logical integrity. You could target the ciphertext, right, and then kind of essentially randomize 128 bits because it's going to decrypt incorrectly. But you also need to bypass the integrity check. So in the case of crypto integrity, you have to essentially brute force this 28-bit HMAC, but if it's incorrect, the trust domain dies. So you get one shot. So that's probably not viable. The logical integrity obviously looks more interesting because there's just a single bit here. So there is another protection that's not shown here. You can turn on ECC, right? So ECC significantly raises the bar for Rowhammer. It tries to protect against silent data corruption by either, flipping the bits correctly and reverting them or signaling an error. But the trick is, what actually turns ECC on? How do you know it's really on? This has to be done by the BIOS. And there's, some uncore registers that it goes and programs and figures out exactly how ECC should be used. And, the question is who actually verifies ECC? If you remember way back at the very beginning, there are these little things called mcheck and ACTM. Those are probably the places that should be checking to verify that ECC is on. But it turns out, when we first reviewed this pre-release, that was not the case. So in that case, a malicious BIOS with Rowhammer capabilities probably could have flipped the logical integrity and compromised the private memory for these TDs. But this has been fixed, so at least that issue is not a worry anymore. Okay. Yeah, so if you go look at the paper, we found vulnerabilities in kind of all these different areas. We covered 3 of them today. And yeah, hopefully this gave you a little bit better view of the ones that we have. So in general, if you look at kind of just things that affect all the different pieces of TDX, the one last topic here, which I think was kind of discussed in some previous talks, are sidechannels, right? So these are kind of just pervasive attack vectors throughout all the different modules in TDX. And we looked at 3 different areas. So we have transient execution-based sidechannels, Spectre, Meltdown, these types of things. And, they do their best, right? So TDX software, it uses the best practices. They turn on all the latest hardware features. This TDX ships with the latest Xeon processor, which is Sapphire Rapids. So, as of publication, they had all the mitigations possible in hardware, and they're all turned on. The TDX software either turns them on or validates that they are on. And they've also placed some manually placed some kind of barriers, speculation barriers, and different things for flush predictors in kind of critical spots. And we went through and validated all this, that it all seems good. But of course, there's always more CPU bugs. So this is where kind of the attestation and upgrading your TCB, these are all part of TDX that is kind of beyond this talk today, but there are ways to kind of verify that you're on the latest and greatest. There's also just traditional timing-based attacks. Some of this was running the crypto library. They use an Intel library, and we went and did some timing validations there. There's an Intel feature called RAPL, which basically makes the power monitoring less granular. So if you're trying to do power analysis attacks from the CPU, not physically attached, but from the CPU, this feature is enabled by the TDX module, and it prevents, or at least makes those attacks much harder, right? There's not enough resolution. In the last bit, I'll talk a little bit more about our access oracles. I think Cfir mentioned this as well. These are host visible effects that disclose some information about the TDs. And in the case of confidential compute, any information about the confidential VMs, leak is even more important than normal, right? These are supposed to be completely opaque VMs, and nothing comes out. So we had 3 different access oracles that I'll talk about here. And so they kind of have different effects and different resolution, right? And they have different ways of going about this. So the first one is, I think Cfir mentioned there was something similar in SNP. You have a way where you can basically unmap memory and block memory access from the TD. This is just that TDH mem range block. This is a TD host is what TDH stands for. So this is a host side API the VMM can make to the TDX module and basically remove a page from a TD. Of course, the TG then goes and uses that page, and there's a fault. It's recoverable, but we get a kind of page level granularity resolution here, that we know that TD used that page, and maybe there's some sensitivity. Given some more information about the TD, you might be able to start deducing what happened. The second one is more fine-grained, but has worse side effects. So the way the TDX works is if you go and you tamper with the memory, it doesn't immediately fault. So if you go and you have OS level execution and you just write to the TDX ciphertext, the protected memory, the private memory, it won't fault. But when the TD uses that memory, or if the TDX module uses that memory, you'll get a termination of the guest at that point. So this is on a cache line level due to the way the writes and the metadata are programmed out to the DRAM. So you get finer grained resolution, but now you've terminated the guest, so you kind of get a one-shot. And then the most powerful one that we found is you can use these legacy x86 instructions, monitor mwait, and then basically it does what it says. You run a monitor, you tell it an address that you want to monitor, and then you use mwait to kind of basically just spin. It'll go to sleep on that core and wake back up when someone uses that memory. And it turns out that you can use this to point monitor into TD memory and then get cache line level resolution. And there's no effect to the TD. I mean, it doesn't even fault or anything. There's no exit. So this is very good for Access Oracle. So, if you start thinking about things like crypto libraries that don't use constant access memory, guest activity that you might want to snoop on, like page table activity, these access oracles might give you ways to gain some insight on what the data is they're processing. So yeah, in summary for TDX, everything we found was remediated by Intel. Like Cfir said, we had a great response from them. This was all remediated before the public launch, which was earlier this year. Yeah, and we had a variety of vulnerabilities. Some of them were pretty small, like in the TDX module. A lot of them were kind of smaller things that we found. But some of the ones, like the NPC Motor bugs, would have led to a full compromise. So yeah, in general, I would recommend everyone else to go look at this, right? Intel, which is great, they've published the source and the specs, so you have basically all the information that we had when we did our review, other than just not having the system architects available. But hopefully between our report and the spec, you'll have a lot of good insight into kind of where to go poke next. Also, TDX, there's 2 more versions already published, right, that are kind of in specification at least. There's one that focuses on live migration, one on trusted devices. It's getting more complex, right? Like there's just going to be more and more attack vectors, more and more things to go look at. So overall, thinking back on confidential compute and kind of our 2 reviews, some of the different things that we've taken away from looking for bugs in both of these. The one thing that kind of overall aspect that changes things is, right, what they're trying to do is they're trying to deprivilege both of these confidential compute solutions. They're trying to deprivilege the host, right? Coming from an area where before the cloud provider, if you're on the host, you can just write and read to the VM. There's nothing really stopping you, technically. And now we have more and more layers, right? We have a whole new threat model that removes the host, removes SMN from being trusted. It significantly raises the bar. It's not perfect, but it significantly raises the bar for sure. And we've had a great, I think this shows like a really great success story for hardware vendors trusting security researchers, right, and giving us extra access and letting us do a third-party audit on their solution before it ships. So we definitely encourage more of this, especially with confidential compute. The users, it's not useful if people don't trust it. So they need to be transparent. There needs to be this transparency and additional scrutiny before people will really trust the systems. And some of this has already been open sourced, and that's going to help greatly, I think. Like I said on the last slide, so Sidechannels, in this model where the VMs are supposed to be completely opaque, any small leakage is significantly more important. So this is like an important area for future research, really. And as you saw, we already have these there's more and more extensions to confidential compute. It's going to get more and more complicated. And so being able to kind of reason about and make correct assumptions about these systems is going to become very important. And basically all new, at some point, all new server CPUs coming out are having the support for confidential compute. So like today, when everything runs in VTX or SVM, it's not too far off, I think, before everything will just have confidential compute on by default. And so this is something that we should be looking into and making sure it's ready to go before then. With that, I think I'm done, and we'll take questions if there are any. Yeah. I'm trying to remember now how we definitely looked into this. Yeah, I don't recall right now. Find me afterwards. We can think about it and see if we put something in the paper. Oh, yeah. Sorry. Yeah. With the memory, for Intel it was AES XTS, I believe, with an HMAC. I don't know how, I don't remember. Yeah, I think it was the same, it sounds like, for S&P. I believe, I don't know if we had any concerns with this when we were going through it. Kfir mentioned performance considerations were why they went with this path. All right, thank you.